And it doesn't have to be limited to just two equations, but for right now I'm just going to limit it to the variables x and y. Okay, so for a system of linear equations, say we have in two variables, say we have a of 1x plus b of 1y is equal to c of 1 for the first equation, and for the second we have a of 2x plus b of 2y is equal to c of 2. Okay, and for this system, okay, if there is one solution, it could be no solution, it might be an infinite number of solutions, but if I have one solution, if there is one solution in the system, if there's one solution in this system, the graphs of these equations will intersect at the solution point. Which is going to be x, y. So you're looking at the values of x and y that will fit into both equations in the system. And now where we have in terms of specified cases, say for a two equation system, say if we're looking at solving for x and y, we'll say that for the first system, we're looking for the values of x and y, and we'll say such that 3x minus y is equal to 3. And also where we have x plus y is equal to 5. Okay, so we got 3x minus y is equal to 3, x plus y is equal to 5. And we can use like a process of elimination through what is often referred to as the method of addition. And if you notice, we got 3x and x for the first and second equations. And if you notice for y, we have a negative y in the first equation, positive y in the second, and you already have additive inverses with negative and positive y. And so what I can do here is that I have the capacity to add the equations and one might ask, okay, why am I doing this? Well, adding them, I'm going to have y eliminated, and this will create the opportunity for me to go ahead and solve for x. So you're going to have 3x minus y is equal to 3. And I have again that x plus y is equal to 5. And if I add the equations, now I have negative and positive y to go out. So here I have 3x plus x is going to make 4x. And 3 plus 5 is 8. And if I solve for x, so we have dividing by 4. Okay, so I have that x is equal to 2. So I have half the solution with x at 2. And I can take 2 and put in place of x and solve for y. And I can choose either equation from the system to work with. And I'll just go with the second one. So in the process, okay, so I can plug in 2 for x and solve for y. So if I just choose this equation, but I could have chosen the first one. Go with x at 2. So I have 2 plus y is equal to 5. In this case, we had that y is equal to 3. You can always double check, so you have x at 2, y at 3, 2 plus 3 is 5, and also 3 times 2 is 6, minus 3, 6 minus 3 is equal to 3. So we have, in the case of the solution, okay, so if I draw out distinctly, okay, so you have x equal to 2, y is equal to 3, and if I were to put as an ordered pair, okay, we have the solution point is going to be at 2, 3. So that's saying that the graphs of these equations would intersect at that one point. Okay. So the first case is where you can arrive at least to the solution of one variable through the addition method, and then the second variable, again, just looking at substituting for the already solved variable. And let's say that if we have second case here, and let's say that where the method of addition is not quite so automatic. And let's say that for this system, we can say that we have x plus 3y is equal to 5, and where we have 3x minus 2y is equal to negative 18. All right, so I have this system of equations. And if you notice, we do not have additive inverses. Okay, have x and 3x, no elimination if I add directly together. And while I have positive and negative y terms, once again, we have 3y and negative 2y. They don't cancel each other completely either. And what you can do is that in this particular situation is that we can eliminate either x or y and solve for the other variable. In other words, by rewriting either or both equations. Okay, now the first case I was able to eliminate y, but things were already arranged where I could just keep the equations as they were. But now I can rewrite this equation where I can eliminate either x or y terms through either adjusting the first equation or second equation or both equations. So, but I think what I'm going to do here, and I think this is going to be the simplest route. Okay, we have with the x terms, we have x and 3x. Okay, now if I were to eliminate the x terms, okay, now you've got 3x, okay, has a higher absolute value coefficient, and I can adjust x to where I can get the 3x eliminated, but there has to be an adjustment with the first equation. Okay, so what is going to take out 3x? It is not going to be x or negative x, but negative 3x. So if I'm looking at, say, eliminating the x terms, what I can do is I can multiply the first equation by negative 3 while leaving the second equation untouched. So if I multiply the first equation by negative 3, we have negative 3x minus 9y is equal to negative 15. And keeping the second equation untouched. Okay, so I can add the equations together. And for what we have now, so I got negative 3x plus 3x. These terms go out. Negative 9y and negative 2y will become negative 11y. And we have negative 15, and negative 18 will be negative 33. And I can go ahead and solve for y. And so we have for y itself. Okay, so y is going to come out to 3. So I have half the solution. Okay, where I have, once again, y is going to be at 3. And what I can do is I can go back to the system and solve for x. Okay, so I can plug in 3 for y in either equation from the system. Then we'll go with the first instance. I already have x present, but I could do it with the other. So plug in 3 for y. And solve for x. Okay, we'll go with x plus 3y is equal to 5. Okay, so I have x plus 3 times 3 is equal to 5. Then we have the x plus 9 is equal to 5. And from this, okay, we'll have the x is equal to negative 4. And so just looking at what we have for the results to check for at least the consistency. Okay, so x is negative 4, y is at 3. 3 times 3 is 9. Negative 4 plus 9 is 5. With x at negative 4, and again, y at 3. We got 3 times negative 4 is negative 12. Negative 2 times 3 is negative 6. Negative 12 minus 6 is equal to negative 18. So those values of x and y will work for both equations. So we're going to have for the solution, okay, so we can say we have x is equal to negative 4. And y is equal to 3. And again, if you were to display as an ordered pair, we have for the points, we would have negative 4, 3. Okay. Now for both examples, okay, I had like the x and the y terms on the same side of the equation. And that might not always be the case. And there are some alternative methods that might be used outside of the method of addition or elimination. And this is what we have for what could possibly be referred to as the method of substitution. And just as an example, okay, say again, if we're looking at solving for x and y, and we can say that, let's say if I have okay, solving for x and y, I'll say that for this system, I'll have the first equation will be given in terms of the slope-intercept form. So I'll just say that we have y is equal to 4x plus 3 They have the x and the y terms apart from each other, and we're still looking at the same values of x and y, where also you're going to have the x plus y is equal to 13. Okay. So you're looking at the same x and y values that will ring true for both of these equations. So just looking at what we have now. Okay, first equation, we have y isolated. We have y is equal to 4x plus 3. And again, I have x plus y is equal to 13. Okay, now where the substitution comes in, okay, from one equation, if I have a variable isolated, I can substitute for that variable in the other equation. And what I mean by this, for y is equal to 4x plus 3, guess what? Y is going to be the isolated variable. And that which is isolated, I can substitute for in the other equation. So what I mean by this, you got y is defined as 4x plus 3. And that which is isolated, I can substitute for in the other equation. So here, I can take the x expression that defines y and substitute y in order to solve for x first of all. Okay, substitute for y, solve for x. And if I do this, okay, so I have x plus, in place of y, okay, so I have 4x plus 3. That is equal to 13. And I'm using the parentheses just to signify that this is what I have replaced y with. And this is with the defining it as 4x plus 3 from the first equation. Okay, so upon adding together, okay, so we have x plus 4x is going to make 5x. Okay, so you have 5x plus 3 is equal to 13. And for what we have in following through, so take 3 away from both sides. So we have 5x is equal to 10. And with division by 5, we'll have the x is equal to 2. Okay, so you have half the solution with x at 2. Okay, and with x determined, okay, I can now determine what y is going to be, and it's going to be through plugging in 2 for x in either of these two equations. Okay, x is solved for it, and now I have the capacity to solve for y. Okay, so plug in 2 for x. And solve for y. Okay, so y is equal to 4x plus 3. Okay, so the y is equal to 4 times 2 plus 3. Four times 2 is 8, and 8 plus 3 comes out to 11. Okay, so I have x at 2, y at 11. I can always go back and check. So if x is 2 and y is 11, well, we've got 2 plus 11 is equal to 13. With y is equal to 4x plus 3, again, we got 4 times 2 is 8, 8 plus 3 is 11, and y is equal to 11. So these values do check out. And so we have for the solution, okay, so we have x equal to 2, and y is equal to 11. We have with the ordered pair, so this can come out to 2, 11. So the graphs of these equations would intersect at that ordered pair. Okay. And again, there will be different types of systems, and you can have also the result to consist of more than just one point in the solution. And let me kind of cap things off, okay, where we might have a system of nonlinear equations. And let me give you just remaining example. And let's say that we have say if I have as a system of nonlinear equations, and say if you're looking at solving for x and y, and we say that for what we have in x and y will be such that if you take the sum of the squares, we're going to have 61. And also, if we have the difference of squares, like we have x squared minus y squared, this will be 11. So you're looking at the values of x and y such that the sum of the squares will be 61, and where the difference of squares will be such that x squared minus y squared is equal to 11. Okay, now I already have additive inverses with positive and negative y squared, so we can go ahead with the method of elimination or the method of addition. So in this one, okay, so I got x squared plus y squared, okay, is equal to 61. And I have x squared minus y squared is equal to 11. And if we look at adding the equations together, so that positive and negative y squared will go out. And x squared plus x squared is 2x squared. 61 plus 11 is 72. And with division by 2. Now we got that x squared is equal to 36. And I'm looking at solving for x and y. Okay, so I got x squared is equal to 36. And I could express as a quadratic equation in standard form, but what I'm going to do here is just use the square root property of equality. So just going from x squared to x. And where I have x equal to plus or minus the square root of 36. Okay, so we have two solutions for x, one positive and the other negative 6. All right, and looking at solving for y. Okay, and so I have both equations with x squared. Okay, and so for what we have in this particular instance, okay, so I can take either equation and just plug in 36 for x squared . And if I do this, okay, so we got x squared, okay, so that's going to be 36. Now 36 plus y squared is equal to 61. And if I take the difference, subtracting 36 from 61, I'm going to have that y squared is equal to 25. And just as I went from x squared to x, I'm going to go from y squared to y. Again, utilizing the square root property of equality. So we have y, we have plus or minus, okay, the square root of 25. And so we had a y is equal to plus or minus 5. Okay, so we'll have, at least in the case of the solution set, okay, just kind of using compact notation, you have x equal to plus or minus 6, and y equal to plus or minus 5. And if I were to express as ordered pairs, so you have like one combination where both x and y are positive, two combinations where I have one positive, the other negative, so you have like 6, -5, as well as -6 and 5. And we have with the remaining combination, okay, so we'll have -6, -5. Okay, so I have 4 solution points. Yeah, so I got x squared plus y squared is equal to 61. So we have a circle that is formed with the center at the origin. Now for x squared minus y squared equal to 11. Okay, we have what's referred to as hyperbola. Okay, and the points of intersection will be the solution sets for what we have in x and y. So we have at this point, I got -6, 5. Another intersection point where we have both x and y negative, so we have -6, -5. And the solutions where x is positive, we got x at 6, y at -5. And also we have where x and y are positive, respectively at 6 and 5. Okay, so this is just a visual construct of how the solution to this system of equations will appear.